So to remedy some of the problems that we've seen in the previous video, we'll introduce a new type of RNN called Lstm, which stands for long short-term memory RNN, because it can take care of long-term dependencies as well as short-term dependencies by using a very interesting idea, right? So before we go into LSTMs, let me revisit this diagram that we have for a simple RNN, right? For a simple RNN. So I'll just draw this diagram where we have two inputs, right? We have XIT, right? And we have OT minus 1 from the previous layer. And we said we'll sum up both of them, right? We said we have two weights here. We have weight W dash and we have weight W here. So we multiply this output with this weight. We multiply this input with this weight and sum both of them up, right? We're just simply summing this up. And then we have an activation unit F, right? Which generates our OT. And this activation unit, we will send it to this activation unit. We can send it to another function G, which will generate our YIT hat, right? So this is the structure that we have seen. Let's redo this structure. So this is one possibility, but there is a slightly modified version of this that I want to walk you through, right? So let me draw the modified version first. The modified version looks like this, right? The modified version looks like this. I have my XIT here and I have my OT here, right? And I have my two weights, W dash and W. And let's write the equations here. The equation here is my OT is F of W multiplied by XIT plus W dash multiplied by OT minus 1, and my YIT hat is it's G of, so I also have weights W 2 dashes here, right? So I have W 2 dashes OT, right? These are the functions that I have in this. This is the model that we have seen earlier. This is the model we have seen earlier. Let's modify it slightly, not a big deal, a small modification, right? Here, what are we doing here? We are multiplying OT and OT with W dash, XIT with W, but instead of adding these two things up, let's merge them. Let's merge them. This operation is called merging. We are merging both of them. I'll explain you what merging is exactly in a second. We send them to our F, we generates our OT, right? And of course, we have our G here, which generates our YIT hat, right? Here there is a small change. What does this merge operation mean? Look at this step. What are we doing? We're taking this, we are merging. We are not adding. We don't have the plus symbol that we have here. What does this mean? So let me write down the equation so that you'll understand them. Okay, what are we doing here is my OT is F of, I will concatenate these two vectors. So I will create a vector which is XIT, OT. I'm concatenating these two vectors and I'm also concatenating the corresponding weights. So this is a vector and this is a vector, right? I can concatenate these vectors. So if this is one vector, this is the other vector, I'm concatenating these vectors. So this vector is my XIT and this vector is my OT. This is called concatenation, or just adding one after the other, not summing, not the numerical sum. This is called concatenation operation. So what I will do here is I will take my newly formed vectors. This is one vector and this is another vector, right? So I will do a dot product between these two vectors, W dash comma W. This is a new vector. This is a new matrix. I'm sorry. This is a new matrix. This is a vector and this is a new matrix. This is a new matrix of weights, right? I'll multiply it with my XIT and OT. Okay. This is equivalent to, see, this whole thing, instead of the sum operation, I'm concatenating my W and W dash. I'm concatenating my XIT and OT minus 1. Sorry, OT minus 1. This is supposed to be OT minus 1. Sorry. Okay. So this gives me my OT. And what about my YIT hat? My YIT hat is nothing but G of, right? My W 2 dashes is still here, right? It will still remain my W 2 dashes OT. So the only difference here is we are summing up here, we are multiplying them, we are doing matrix vector multiplication and then summing up. Here Instead of summing them up, we have concatenated these two vectors and created a larger. See, this matrix is larger than W dash and W. This vector is larger than XIT and OT. This is also a simple RNN. This is a slightly different, modified version of a simple RNN. Both of them are used, but we'll stick to this notation so that we can understand LSTM better. Right? This is a preferred way actually nowadays. Right? So for this discussion about LSTM, there is a terrific blog by Christopher Olah. If you recall, we saw a lot of blogs by Christopher Olah, especially the Tsne blog. We understood a lot about Tsne from Christopher Olah's blog. Christopher Olah is now a research engineer, or I think he's a research scientist or research engineer at Google working on their deep learning stuff. Okay, so let's understand. So this is his blog, terrific blog. It's written in August of 2015. I really enjoyed reading this blog when it was first published. It is the best blog I've read about LSTMs. Actually, my understanding of LSTMs have improved dramatically after reading this blog. Or I should say they've become much more clear. A lot of times what happens is when you first read a research paper, you get an idea of things, but you still have some lagging doubts. It's still not fully clear for you. My clarity about LSTMs really improved after I read this blog. It's a brilliant blog. The notation here is slightly different from the notation that we are used to. So let me connect the dots here. Okay, here what you have is xt. Here what you have is xt, what is same as what we used to write as XITs. Okay, this is your input. This is your input, right? What we write as outputs, right? These outputs, right? These are written as CTs. The outputs which go to the next stage are often referred to as CT in this blog. Okay, I'll just connect the dots. CT is nothing but our OT. Remember, our input is XT, which is now our XIT is what is written as XT in this blog. I'll just introduce you to the notation in this blog and then we'll go down. I don't want to confuse your notation. So our OT that we have seen, what is OT? If you look at this, OT is what goes as output from one RNN, from one step to the other step, right? That is called as CT in this blog. And the output that I have, my YIT, what I call as YIT, is called as HT in this blog. Okay, simple things. My YIT becomes HT, my XT becomes XIT, my OT becomes CT, and the names are very interesting. X is for input, C is for cell state. So when they say C, it means cell state. We'll see why it's called cell state, because this is the state that is being transferred. Look at this. This is CT minus 1. This is CT. This is CT plus 1. So this is the state of the cell from one time step to other time step. So this is called a cell now. So each of these units is called a cell. What we call as one activation unit. What we call as activation unit. Right? This is the block diagram, right? It's also called as a simple RNN cell. So you see this word cell used a lot. Right? So CT is called the cell state. It is a state of the cell from one time step to the other time step that is being passed out. These HT is your outputs, right? So with this notation, we'll continue. There are a couple of things that I should tell you. Whenever two arrows join here in this notation, in these diagrams, it means that you're concatenating the weights. So look at this. What all weights do we have here? We have our W here. We have our W dash here. And we have your W double dash here. Right? You have three weights here, right? Literally. Now look at this. So when I apply this operator, what does this mean? It implies your concatenation operator the way we have seen here. So this is when you combine two lines like this, coming from two inputs with two different sets of weights, you're simply concatenating the weights and the inputs. That's what it means. That's why I've introduced you to this notation, to this way of writing a simple RNN, so that it will be easy for us to understand this block. This block is the best block I've seen. That's why I'm focusing so much on this. Now, if this is our simple RNN, very simple standard RNN, our LSTM looks like this. Don't worry about this. There are lots of pieces here. I'll explain you one by one. The first time you see this, you're like, wow, there are so many operations here. But I'll explain you one by one. Okay. So this is how, so this whole structure that you see here is what is called an LSTM cell. Okay. And this is at time step t minus 1. This is a time step t, this is a time step t plus 1, so on and so forth. Again, this axis here is the time axis. Okay, and the reason they have this complex structure, we'll break this up step by step and understand, right? So there are a couple of, there is simple notation that I want to introduce you to. We'll break this up. I'll explain each of these connections. So whenever you see a yellow box here, it means a neural network layer, like a sigmoid. Like this is a sigmoid unit, this is a sigmoid layer, this is a tanh layer, this is a sigmoid layer. Whenever you see a pink box like this, it means point-wise operation. So when you see this, what it means is, if you have a vector and another vector with this operation, right, with 3 by 3, you multiply the first one with the first one, you multiply the second one with the second one, you multiply the third one with the third one, and generate a 3 by 3 vector. It's called point-wise. It's called point-wise operation. Or corresponding elements are multiplied one. The first element is multiplied with first element, second element with second element, third element with third element, and generated, and these values are generated. Similarly, you have a point-wise addition also, right? Very, very simple. And this is a point-wise tanh. So this is not a layer. Remember, this is not a layer. This tanh is basically, if you have a vector, let's assume you have a vector, you are applying tanh function on this to generate a vector now. So this is, you take this input, send it to tanh, and you generate the first output. You send the second input to tanh, generate the second output, so on and so forth. Again, this is a point-wise operation. This is not a layer. Very, very important. This tanh in the yellow box is a layer of tanh neurons, right? It's basically a layer of tanh neurons. Very, very important. A lot of people miss that. A lot of people think that this is also a tanh layer. No, this is a point-wise operation. So everything which is pink is point-wise. Everything that is a yellow box is a neural network layer. And this is a simple vector. So when you say this vector is basically going from here to here. So when two vectors are joined like this, it means concatenate operation. Right? When two vectors separate out like this, it means copy. See, this value which is here goes both to HT and to the next one. Right? So that's what it means. So look at all the inputs that are there. So that's the next thing we have to understand. Right? So this is HT, right? This is your HT, and we'll go. So this might look too daunting initially. I'll explain you what these two inputs are, what these two outputs are, what this output. Look at this. Unlike your simple LSTM, simple RNN, you have two inputs here and two outputs here. Unlike that, here you have two inputs. You have two inputs and the third input. You have three inputs, and you have this output, and this output. We'll see what they are. Don't worry. You have three outputs and three inputs. Here you have two outputs and two inputs. We'll understand what they are very, very slowly. Let's go step by step. So let's take the first line. So in this whole diagram, let's break it up into various paths and explain and understand each of these paths. Okay, let's take the first path here. Okay, let's look at the variables. Let's take only at one unit here, right? So this is one LSTM unit, and you have three inputs. Let's write down what are the inputs. The first input is called CT minus 1. Is CT minus 1, which is, look at it in our notation. What is CT minus 1? It is OT minus 1. I'll just write it so that you understand. This is a cell state from the previous cell. This is, look at this. Here you have something interesting. You have HT minus 1 here. What is HT minus 1? HT minus 1 is nothing but YIT minus 1 in our notation. Okay, two inputs. And of course, you have your XT here. All these three are inputs. So you have, what is XT? XT is XIT. You have the word at the current, you have the word at the teeth. You have the teeth word here. You have the output from the previous stage. You also have the YIT from the previous stage as input. So there are three inputs. So in this case, what's happening? This is again going as input to the next layer. This output is going as an input to the next layer. So this is one input. This is one input. This is one input in an LSTM. Okay, what are your outputs? Because the HT, CT, and HT, even though there are three outputs, there are actually only two outputs. You're copying the HT, you're sending it here, and you're sending it to the next stage also. Even though there are three output arrows, there are actually two outputs, CT and HT. And what is HT here? HT is nothing but YIT. What is CT? It's nothing but OT. Right? So look at it. Even though in this above diagram, you see that there are 3 inputs and 3 outputs. Look at this. This is an input, this is an input, this is an input. This is an output, this is an output, this is an output. But this output and this output are the same. Right? It's the same output that is going without any, so this is like a hop. Okay, it goes up, it doesn't do anything, it goes up. So even though you have 3 inputs and 3 outputs, what you really have, even though the arrow shows that, you have 3 inputs, CT minus 1, HT minus 1 and XT, and you have 2 outputs, CT and HT. To put it simply, this is a cell state from the previous stage, this is the output from the previous stage, or in other words, this is the YIT. This is the YIT minus 1 from the previous stage. This is the input in the current stage. This is a cell state in this, at the end of this stage. This is the YIT in this stage. Okay. So there is a different notation in here as compared to what we have seen here. So it might take you a couple of seconds to get used to it because we are used to the OT, YIT, XIT notation. But it's okay. Just flow with me, please. Okay, because the reason I could have drawn all these diagrams on my own and explain it, but I want you to read this blog later. That's why I'm explaining it with the notation that is there in this blog. This is the best blog that I've seen, right? Okay, so let's look at this connection. What does this connection do? Okay, let's ignore everything else. Let's ignore everything else. What does it do? I have my cell state coming from previous timestamp, and I'm sending it to the next timestamp. Now this output that I got from the previous stage, right, from t minus 1 stage to t stage, I have a pointwise multiplication operation here and a pointwise addition operation. If my pointwise multiplication operation is a vector of all ones, right, and if my pointwise addition operation is a vector of all zeros, what happens? Then my CT is equivalent to CT minus 1, because whatever vector I got here, if I multiply every element by 1 and add 0 to it, I get the same element. I get the same element here. Right? This is very important. So what is actually happening here is, whatever is the cell state before, I can send it out as the cell state as is if I want to. Right? If this value that I'm sending here, if this value that I'm sending here, and if this value that I'm sending here, if this is all ones, if this value that I'm sending here is all ones, and if this value that I'm sending here is all zeros, then whatever is the value of CT minus 1, the vector, the same vector is literally copied to the output. This is like an identity. Look at it, this becomes like an identity. If and only if the input that you get from here, this input is called FT. Okay, this input is called FT. If this FT is all ones and if this input is all zeros, if the input that you get here, if this vector is all zeros, if this vector is all ones, right, if this vector is all zeros, whatever I have here, there is an identity mapping. Just recall what we have done, something similar, right? Remember our rest nets, our residual nets in convolution neural network? We learned rest nets, right? What did we do in rest nets? You have these connections, but there is a way for me to jump from here to here. I can skip over layers through an identity. Right? This was called the residual. Remember, this was called the residual unit, or the residual block, or it was called the identity block. Recall what we learned in ResNets. What did we do? We had a mechanism for us. We had a mechanism where I can jump over layers and just transfer the whole identity. So when I first learned about LSTMs, I think not when I first learned about them, because I was learning these concepts almost parallelly, right? So I saw a lot of similarity between what ResNets were achieving and what LSTM was doing, because this is an identity mapping. But of course, LSTM is far more complex because you have this point-wise products and point-wise additions, which you don't have here. You have weights here, in these layers, right? But I saw that there is an identity mapping that is possible in ResNets, just like in your LSTMs. So this is something that I first thought was very, very interesting connection between these two. Of course, there is no direct connection between both of them, but it's a nice idea to learn. It's like a common theme, having an identity mapping. Like if you were ever to design your own networks, Identity mapping is something that has been used already twice, like here, also in RESTnets, right? Okay, back to our topic, back to our discussion here, right? So this is called, so what is happening here? The state of the machine, the state of my LSTM from one time step to other time step can be carried as is if I want, without any changes. But if I want to change it, I can change it, right? Suppose if this vector, suppose I have a vector here. So let me just write some numbers. Suppose I have a vector here, 2, 3, 4, 6, 8. Suppose if this vector here was all halves, okay, and let's assume the vector here is all halves. The vector that I have here is, let's say, all zeros. Then my CT becomes, right, half of this. So I get 1, 1.5, 2, 3, 4. So I can decide how much of my previous cell state do I want to remember to the next state, right? That's what this FT tells me. This tells me how much of the previous state, what percentage of the previous state should I remember to the next stage, right? So this is literally like a forget thing. How much should you forget? Or how much should you remember actually? Because if it is all once, look at this. If it is all once, if this was all once, you are remembering everything. Whatever is here, you're remembering everything, right? So this is like a forget. This is often called as a forget gate because it tells you, or it gates how much information should go from here to here, or what percentage of information should go. Here you're adding more information to the cell state. We'll see this network later. To understand. So this is like a forget gate which says how much of the information from the previous cell state should you retain to the next cell state. That's what this literally does. And this says how much new information should I add after I have remembered some part of it, right? So, but most important thing is you can skip over connections. That's very, very important. Okay, so let's look at this part now. Okay, so let's walk through. So this is called, so this is one part. So we have seen the top part, right? We have seen the top part. Now let's go and understand this part. Okay, so this part. Okay, so let me go here. Okay, this part. It takes two inputs. It takes HT-1 and XT. It concatenates both of them. And there is a simple sigmoid layer. And it says FT. So to write it in mathematical form, my FT here is sigmoid of a bunch of weights. Okay, I have to see this WF is basically two sets of weights. One set of weights from here, one set of weights from here, one set of weights from here. Okay, if I concatenate these weights and these weights, I get WF. This is called forget gate weights. The weight that you have here and the weights that you have here. You concatenate both of them to get WF. Similarly, you concatenate your HT-1 and you concatenate your XT. This is concatenation operation, right? And you are adding a bias here. This is like your W transpose X plus B. This is a bias term, right? So your FT, mathematically speaking, is the sigmoid of the forget gate weights. So the weights that you have here and the weights that you have here, right? If you concatenate both of them, you get the forget gate weights. And this is called the forget gate. And this is the forget value. How much of the previous value should you forget before you send it out? Okay, it's called the forget value, right? Sounds good. You have these weights. So this part of the equation is simple. So we are done with this layer. So with this connection, we are also done with this connection. So this is called the forget gate. It tells you how much you should forget or retain from the previous cell state to the next cell state. Next comes the input gate, which is this structure. In this structure, what are we doing? We are saying IT here. We are saying IT here is a sigmoid unit of WI. Again, I have weights here, right? I get this and this are merged together. When I merge them, I get a weight WI. This weight is the weight input to this sigmoid, right? My WI. This is called the input gate. This whole structure that we are seeing is called the input gate. This whole structure that we are seeing here. Let's write down the equations. Now the final output of this, so look at this. This structure tells us how much from the previous state should you retain or forget. This one says how much should you add to the previous stage, because there is a plus operator here, right? So this whole structure is called input gate because it says amongst the input information that you have, how does that impact how you change your input or cell state, sorry, how you change your cell state from t minus 1 step to to tth step. The equations are straightforward, right? Your IT is sigmoid of the weights. You have two weights here. This is called the input weight gates, and you are concatenating ht minus 1 and xt, and you're adding a bias, right? The next one, this CT is, see, you concatenated both of them, and you have another layer here. This layer, these weights are called WC. WC, you concatenate both of them, and you're taking a tan H layer on top of it, and this is called CT hat. Now I do a element wise or component wise multiplication of both of them and decide to add that. So let's go there. Let's write down the whole equation, right? So my final equation, my CT is FT multiplied by CT minus 1. This is point wise multiplication. Okay, when I say this star, it means point wise. Take every element of CT minus 1 and take every element of FT. You do point-wise product, right? You do a point-wise product. This is nothing but what you get here, right? What you get here. Then you add, because you have a point-wise addition element here, you add IT and CT tilde. So literally what's happening here is, this is your previous state. This is your state that is at the end of the stage. This is the previous stage, and this is the current state of your, it's a cell state. This tells you how much you should remember or forget. This tells you how much should you add to the cell state from this stage to the next stage based on your inputs, ht minus 1 and xt. So this stage is over, this circuit is over, this circuit is over. We are left with this circuit, right? So this is called the forget gate. This is called the input gate structure, and this is called the output gate structure, because this structure defines what your output is, which is your ht, right? So there are three layers here. I'll come back to the layers again. This is very straightforward again. So you have these two, you concatenate both of them. You have weight W0 here. This is called the output weights. And you have a simple sigmoid on top of it. You get OT here. This OT is not ROT, okay? It's a different notation here, okay? And finally, you're saying, you also get some CT here, right? You get your CT here. Because you've done all these operations, you get your CT. Your HT is dependent on your inputs. Your output in this layer is dependent on your previous output, right? Your current input and your previous cell state. Modified, your current cell state literally, not your previous cell state, your current cell state. Because your previous cell state has already been modified here. So what are you literally doing here? Your HT here, your HT, which is output here, your HT here is the point-wise multiplication of the tan H of CT. You're taking your CT and you're doing a tan H of this. So the flow is like this. You get this and you do a dot product, point-wise product of the tan H value of this, and you send it out to HT. And the same value is copied and sent out this way also. So you have only two outputs, CT and HT, except that HT goes here. See, if you have multi-layered RNN, right? If you have a multi-layered RNN, you might have to go, we'll show how deep RNNs work in one of the videos, right? So if you want to go multi-layered structure here, right, this goes into the next layer. Okay, very, very simple. So overall, let me give you the overall picture now. Okay, let me take you to the first step. This basically says how much from the previous cell state should go to the next cell state. This is your forget gate, this is your input gate, this is your output gate. Your input gate says how much should your cell state be modified based on your inputs. This basically says your output should be generated based on the current cell state, because CT is already here, and your previous and the current stage inputs. Okay, that basically, this is forget, this is input, and this is output. The most important thing here, remember the problems that we saw in the previous stage were long-term dependencies, did not work well. But in this case, because I have a way to short circuit everything, because I have an identity mapping here in the cell state, right? If this vector ft was all ones, right, and if this was all zeros, I have a way to have a simple identity mapping here. Just like in ResNets, if this whole block was useless, Remember, if this whole block was useless, the regularization would simply kill it and make you jump layers. Even here, if this whole structure was not useful, if this structure is not useful, it will ensure that you will simply pass your CT-1 to CT. So long-term dependencies are possible because you're able to retain the cell state. You're able to retain the cell state. What is CT here? CT here was OT in our mapping. CT was OT in our mapping, right? So look at this. Here we said there is this problem of long-term dependency, right? This is O1, this is O2, this is O3, this is O4, this is O5. But because I have an LSTM-like mechanism, instead of simple NNNs, okay, let me draw it actually. I think that's better. Okay, imagine I have a structure like this. I have xi1, right? And I have xi2, right? And I have xi3 and xi4, right? And this generates, let's say, yi1 and yi2 and let's say yi3. Okay, this is my encoder part, this is my decoder part, right? Now we said if this depends on this, because they're very far away, in a simple RNN, because I have lots of values here, they're very far away in terms of relationships, and because of vanishing gradient, everything can go crazy. But what are we doing here? We have O1 here, we have O2 here, we have O3 here, we have O4 here, O5 here. Instead of simple RNNs, if you had LSTM RNN, if each of these units were LSTM, if there was a dependency between this and this, okay, now remember, this is very dependent on this is very dependent on this, because they're just right at the same layer, at the same timestamp, in the same iteration. O1 depends a lot on xi1. Now, if these layers are all useless, right, in my O1 is nothing but, remember, what is O1? O1 is nothing but my C1. I can skip over these connections. I can literally pass through these connections and pass O1 as an identity here. Thereby, I have a way to have long-term dependencies worked out because of this short circuit connection. This is like a short circuit connection if you want. So I can actually jump over, I can have this short circuit connection to make my O1 flow through. My O2 can be exactly same as O1, right? Because if this was ones and these were zeros, right? If ones come in here and if zeros come in here, what do I get? My O1 will pass exactly as O2, O2 as O3, O3 as O4, and O5. My O5 can be exactly equal to O1 if it need be, right? Then I know that O5 impacts my yi3. Look at this structure. My xi1 impacts my O1. My O1 can short circuit through and become equal to O5. My O5 impacts yi3, which means now I have a mechanism where I can impact something which is very far away because of the short circuit connection, because of the possibility of having a short circuit connection. I'm not saying short circuit is always there. If there is a relationship between this output and this input, which are very far away, this is like a long-term dependency. Still that can be achieved because of this connection. This is the innovation, I would say. This is the big innovation of LSTM. And remember, LSTMs were created in 1997. So this is a great feat of engineering and innovation. This is prior to deep learning. So there were, even when deep learning was not very popular, there were a bunch of researchers, especially in Canada, like Jeff Hinton, Yan Lee Kuhn, etc., who are continuing to work on some of these great ideas. And the core LSTM design is as old as 1997, but it really became popular only around 2014 and 2015, because now it could solve very interesting problems like speech recognition, like NLP problems, etc.